Hello everyone, welcome to this channel. If you're new here, my name is Hasan. Let's begin our 19th part of the video series. Today we'll be discussing about the concept of power in lenses. Okay, we have already discussed the concept of focal length. So focal length and power are related. So if you haven't checked my earlier video on focal length, then please do check that video. And today we'll be discussing about the power in convex lens and concave lens. Then we will jump into the concept of power in mirror. So there's a little bit different when it comes to the concept of power in mirror. So we'll be looking into that, and then we'll be jumping into the combination of lenses, how to find out power when thin lenses are combined together. So this concept has already been discussed in my earlier video. So it's just an extension of that concept. And finally, we'll be looking into how to find out the power or focal length when lenses are cut into two equal halves, either vertically or horizontally. So this is what we'll be learning today in this video. So without any further delay, let's jump into the concept building process and let's roll the intro. Okay, so let's start our study on the concept of power. So we'll be looking into the definition of power. It says that power is the ability of lens to converge or diverge the path of rays. So as you can see, I have written it down here that greater the convergence, greater is the power, and vice versa. That is, greater is the convergence, greater is the power, and lower is the convergence, lower is the power. Okay, I hope this is clear. In order to explain this, I have drawn this two diagram in order to explain the concept of power. So let's see, this is our lens 1 and we have taken a convex lens, and this is our lens 2, we have taken a convex lens. Now let's analyze. We have taken an object here, and from this object we have taken a ray that is parallel to principal axis. Okay, as you can see in the next diagram also, we have taken a ray parallel to principal axis, and according to the law we know that after refraction, what happens if the lens is a convex lens? Then the rays will converge towards a fixed point, and that point is known as focus, as you can see it here. Okay, so we can see the rays converges to the point of focus, and here also you can see that the rays converges to the point of focus. But if you look carefully, then you'll see that the level of convergence is different for these two lenses. The convergence here is lower and the convergence here is higher. And from the definition, we know that greater the convergence, greater is the power. Therefore, since the convergence that is produced by this lens is greater, okay, therefore we will say that the power of this lens is higher than the power of this lens. I hope this is clear. So this is the basic fundamental concept of power. Now let's analyze the concept of divergence. Like it's written that greater the divergence, greater is the power, as you can see, and vice versa. That is, lower the divergence, lower is the power. And this is true for concave lens, as you can see, because concave lens is a diverging lens. As you can see it here up, what I've written, the definition of power, that the ability of lens to converge and diverge. Okay, so both are taken into consideration. So we'll be looking into divergence now. So similarly, we have taken lens number 1 and we have taken here lens number 2, and we have taken object in front of the lenses, both lenses. Okay, and we have taken rays that are parallel to principal axis for both the cases, as you can see it here. Okay, and we know after refraction what will happen, the rays will diverge, and as you can see it here, the rays are diverging for both the lenses. Okay, but if you look carefully, you'll see that the level of divergence is different for both the lenses. For this lens, we can see the level of divergence is lesser than the divergence here. Here the divergence is bit more than the first case. Therefore, since the divergence is more in the second case, we say that the power of this concave lens is more than the power of the concave lens in the first case. I hope this is clear. So this is all about the fundamental concept of power. Now let's understand one thing, that the converging ability of a convex lens is denoted by positive power, and the diverging ability of concave lens is denoted by negative power. That is, if power is denoted as positive, that means the rays after refraction is actually converging, and if negative sign is used for power, then power denotes how much more the lenses are diverging. Okay, I hope the concept is clear. So you need to remember this. Positive power means the ability to converge, and negative power means the ability to diverge. I hope the concept is clear now. Okay, so please take a note of what I'm saying or what you see on the screen, and things will be very clear. Now let's understand the formula for power. Now power, as you can see, it's written here that power is inversely proportional to focal length. Now how is this coming? Let's look into that diagram and things will be very clear. Now let's look into this convex lens. Okay, now we know that lens number 2 has more power because the convergence is more in this lens. Okay, now what does focal length actually denotes? It denotes the distance from the optical center to focus. As you can see, the focal length for this is this. Okay, so we can see from the diagram that greater the convergence, smaller is the focal length. As we know, for the second case, the convergence is more, therefore focal length will be lower. Simple. If you just understand the diagram, things are very simple. Okay, I hope this is clear that greater the convergence, lower will be the focal length. Okay, because the rays are meeting the principal axis a bit earlier when the convergence is more. Okay, so the focal length will be less. That's why we say that power is inversely proportional to focal length. Okay, if you look into our second concept, that is for divergence, we will see that we know that the lens number 2 has more diverging power, that is power is more for this lens, and we see that the focal length is smaller for lens number 2. Why? Because the divergence is more. Okay, nothing to explain here. If you just look into the diagram, things will be automatically clear. Therefore, from the diagram, we can say that power is inversely proportional to focal length, and we derive the formula that power is equal to 1 by focal length. Okay, this is clear. This is basic mathematics. We just replace the proportionality sign with equal to sign. Now, what is the unit of power? We know that focal length is a length and the SI unit of length is taken in meter. Therefore, 1 by meter is known as diopter because power is nothing but 1 by meter. That is meter inverse. The name for meter inverse is taken to be diopter. Okay, so this is the unit for power, and you need to remember this. Okay, because in your question or numerical they will give focal length in terms of sometimes centimeter or sometimes millimeter. You need to convert that focal length in terms of meter in order to get the unit of power in diopter. Okay, so don't be in a hurry and put the value of focal length in centimeter or millimeter. Okay, you need to put the value of focal length in meter. I hope this is clear. Now let's jump into our next concept, that is the synopsis of the concept of power, and we'll be looking into the power of mirror. Okay, so let's jump into that. Now let's look into this synopsis. I have drawn a table for you in order to make the things very clear so that you can have the concept at a glance. That is, the first column tells us about the lens. Okay, the first lens is convex lens. We know the nature of convex lens is converging. Focal length is always taken as positive because if this is our convex lens, okay, then f2 is in this direction and our incident ray is in this direction. Okay, so this direction is taken as positive, and if this is our optical center, then our focal length is measured in this direction, so focal length is taken as positive. Simple as that. And we know power is 1 by f, so we got power as positive. And I said earlier that positive power denotes what? Positive power denotes the ability to converge. Okay, the ability to converge is denoted by positive power. I hope this is clear. You need to remember this. Don't confuse this. Okay, you'll see the magic happening later if you just understand this concept. Okay, so the next lens is a concave lens. Nature is diverging and focal length is negative. So let me draw it and things will be clear again. And we know this is our concave lens and this is our f2 in this side and our incident ray is in this way. So we take this as positive, and if this is our optical center, then we measure focal length in this direction, isn't it? Therefore focal length is taken to be negative. I hope this is clear because we are going against the direction of incident ray. So we got focal length as negative, and therefore the power is negative. And we have just seen that the ability to diverge is given by negative power. I hope this is clear. So the ability to diverge is given by negative power and the ability to converge is given by positive power. Now let's look into the power of spherical mirror. Why we'll be looking into the power of spherical mirror? Because even spherical mirror has the tendency to converge or diverge rays. So let's look into that, and you'll understand that the concept is actually going hand in hand. Number one, the first mirror is a convex mirror. Okay, now if you look into convex mirror, it's different from convex lens. Okay, what does convex lens do? Convex lens is a converging lens, but if you look into mirror, convex mirror is actually diverging in nature, as you can see it here. Okay, so it diverges the ray, so I've written it convex mirror is diverging in nature. Therefore, as you can see, we know that for convex mirror, focal length is positive. Now why focal length is positive? Because our focal length will be in this direction, that is, this is the focus, and we'll be measuring focal length from the optical center. So the direction of measurement and the direction of incident ray is same, therefore focal length will be positive. Okay, and now the power is taken to be minus 1 by f. This is very, very important. Why? This is taken as minus 1 by f so that when we put the value of f as positive, we will get a negative power, because see, minus 1 by f. Now for convex mirror, f is positive, so we will be putting here positive, therefore we will get minus 1 by f actually. That is, the result will be negative power. Now why negative? Here we got positive, but what does negative power indicates? Negative power indicates the ability to diverge. Okay, since convex mirror is actually a diverging mirror, therefore the power will be negative. But since convex lens is a converging lens, the ability to converge is denoted by positive. I hope now the difference is clear. In the same way, concave mirror, if you look into concave mirror, then we know this is our concave mirror. If this is our concave mirror, then our focus is somewhere here and our incident ray is in this direction. And in order to measure focus, we need to go in this direction. Therefore, we are going against the direction of incident ray. Therefore, focal length will be negative, as you can see it here. So this is established. Now, power is minus 1 by f. So if you put minus of 1 by minus f, because f is negative, so you'll be getting positive power. Now what does positive power actually indicates? Positive power indicates the ability to converge. Okay, now let's understand. So if you draw a ray, then what will happen? After reflection, it will pass through focus. That is, you can see that the rays are actually converging towards a point, and the ability of this convergence is denoted by positive power. That's why the positive and the negative power is flipped here, because the nature of convex and the concave mirror is opposite to that of convex and concave lens. I hope this is clear. So this is how we need to find out the power of spherical mirror. I hope this is clear. Okay, now let's move on to our next concept. Now we'll be looking into combination of thin lenses in contact. This is very simple. Okay, so let's look into this. This concept have been explained in my earlier video about focal length. Now we'll be looking into power, since we have learned power in this lecture video. Okay, now we know that the effective focal length for combined lens is given by 1 by fe is equal to 1 by f1 plus 1 by f2, and I have told you that f1 and f2 should be used with proper sign. Okay, basically what we are doing here is that we are replacing this lens, two lens, with a single lens having focal length fe. That is effective focal length. Okay, I hope this is clear. So this is the formula. It depends on the number of lenses. Since we have used two lenses, so we have written f1 plus 1 by f2. I hope this is clear. Therefore, if we use two lenses, then what will happen? We know 1 by f power is given by 1 by f. Therefore, 1 by fe can be written as pe, 1 by f1 can be written as p1, and 1 by f2 can be written as P2. So simply we can say the effective power of this lens is basically the addition of all the power of individual lens. So PE is equal to P1 plus P2 plus P3 plus P4, and it will go on depending on the number of lens. And what you need to understand is that these powers, the value of these should be used with proper sign. Okay, don't ever forget this. Otherwise, things will be very, very different and you'll get a wrong result. Okay, so this is all about this concept, simple as that. Now let's move on to our next concept. So let's look into this now, that is cutting of thin lenses. What will happen to the focal length, or what will happen to power if we cut the lens vertically or horizontally? So we'll be looking one at a time. So what we'll do is that first of all, we'll cut this lens vertically. So what will happen to the focal length? So if we take this lens and cut this down in this fashion, then we will get these two lenses. Okay, so if the focal length for this lens is f, then what will be the focal length of these two lenses? Okay, this is our task. If we can find the focal length, then power is easy, just it's the reciprocal of focal length. So let's see. Suppose the focal length for these two lenses be f and f. Why both will be same? Because both the lenses are identical, as you can see. Okay, therefore both of them will have the same focal length. So let's see, 1 by f is equal to 1 by capital F plus 1 by capital F. Now you may be wondering how I wrote this. Very simple. See, these two lenses combine to produce this lens. Okay, so you can say the combined effect of these two lenses will be this. So we can use this formula. If this is the combined focal length of these two f, we know from the combination of lens that 1 by fe is equal to 1 by f1 plus 1 by f2. Here f is actually basically f1 and here f2 is basically capital F. So we are just replacing the value of f1 and f2 here. Okay, and we are getting the combined focal length, that is this one. I hope this is clear. So we will get 1 by f is equal to 2 by capital F, or we can say that f is equal to 2f. This is what we actually need. So we know now the capital F, that is the focal length of these individual lenses, will be double the effective focal length from where we are cutting out the lens. Okay, so this is the original lens that is having focal length F. So this individual lens will be having double the focal length of the original lens. So for example, if I say that this focal length of this lens is suppose 6 centimeter. So what will happen if I cut this lens into two equal halves vertically? So what will be the focal length of the individual lens? The focal length of the individual lens will be double the original lens. That is, it will have 12 centimeter. Okay, so this lens will have 12 centimeter and this will also have 12 centimeter. Okay, double. So I hope the concept is clear. So whenever lenses are cut vertically, then the focal length of the new lens becomes double the original lens. I hope this is clear. Now let's move on and check what will happen if the lens is cut horizontally. Like if this is our lens, okay, and we cut this lens in this fashion, like horizontally, then what will happen? Then the focal length, just guess what will happen? Focal length will not change. Why focal length will not change? We know that focal length depends upon 1 by f, that is focal length depends upon refractive index of lens divided by refractive index of the medium in which the lens is kept multiplied by 1 by r1 minus 1 by r2, where r1 and r2 are radius of curvature of the first and the second surface respectively. Okay, so this is the formula for focal length. So focal length depends upon two things, that is refractive index and radius of curvature of the surface. Now when we cut this lens horizontally, then what happens is we are getting two lenses, that is this one and this one, isn't it? Now this lens is having refractive index mu, and if you look and analyze this lens will also have refractive index mu, isn't it? Nothing is changing. Now this is having radius of curvature, suppose r1, and this is having radius of curvature r2. Same way we will have r1 and this will be r2 and it will not change. See, just look into the diagram and you will get it. Okay, so since refractive index and the radius of curvature are not changing, therefore we'll say that focal length will not change, or the focal length for this lens and focal length and of this lens should be equal to focal length of this lens. Okay, this is clear. Then now you may be asking why the focal length of this changed. Maybe any of these parameter has changed while we cut the lens vertically. So let's analyze and things will be clear. When we are cutting the lens vertically, we are getting two lenses like this. Okay, so this is our first lens and this is our second lens. Yes, it's absolutely true that the refractive index of the lens doesn't change, because initially it was made up of glass, now also it is made up of glass. Okay, so refractive index is not changing. The only thing that is changing is r1 and r2. See, r1 is not changing because it is similar to the first original r, but r2 is changing. R2 here is infinite, that is plane surface. Whereas if you look into this figure, this is R2, which is a spherical surface. So since R2 is changing, therefore focal length will absolutely change. Therefore in this case we can see that focal length is changing when we are cutting the lens vertically, but when we cut the lens horizontally, since refractive index not the radius of curvature are changing, therefore the focal length will not change. I hope the concept is clear. So this is how you need to solve question based on cutting of thin lenses. Now once you have understood the concept of focal length, then the concept of power is also simple. So let me give you one question. Suppose this is our lens having focal length suppose 5 centimeter. If we cut this lens vertically, then what will be the power of the individual lens? Then it's very simple again. So if we cut this lens here into these two pieces, then we know the focal length of these two pieces will be double of this. So this will be 10 centimeter. Therefore, the power will be 1 by 10 centimeter. Now you need to convert this into meter. Okay, now if you convert this, then we will get 10 into 10 to the power minus 2, okay, as meter, and then we can get the value of power in diopter. I hope this is clear. So this is how you need to find out power when we cut lenses vertically, and the power for lenses when we cut the lens in horizontally remains same because the focal length doesn't change. I hope this is clear. So this is all about the concept related to power and focal length. I hope the concepts are super simple and you have understood the concept. So this is all for this video. If you enjoyed this video, then please give it a thumbs up, and if you haven't subscribed to this channel, then please consider doing so. Till next time, enjoy your studies and build your concept, and I will catch you all in my next video. Bye bye.